All right, so it's at the top of the hour. Let's just get started. And the first few slides aren't super important, so we'll let others trickle in, um, and they hopefully won't miss much. So welcome, everybody. Thanks for joining us at this webinar on this wonderful Saturday morning. This month's Green Energy Series is we're going to talk about batteries and the fire code. Um, this is a very interesting topic because uh, the world of home battery energy storage systems and their relationship with fire code has recently made some really major changes. And so we'll get into that. So this webinar is provided by Solar Oregon. Solar Oregon is a Oregon nonprofit whose mission is to provide education, outreach, a community, and advocacy related to solar. And we help homeowners and businesses in the Oregon and Greater Pacific Northwest figure out how to go solar and increasingly not only go solar, but to do solar plus storage. Some of our events are solar tours, and then we also do solarized campaigns as well as peer-to-peer education. This organization has been around for getting close to 40 years now. So one such event that's coming up is an in-person event at Ichijo Homes on June 17th from noon to 4. Ichijo Homes is one of the uh, premier home builders that are building homes in the Oregon area. Um, they are a very innovative home construction company. They are one of the few that do panelized walls, so the homes are built with offsite construction, and then the walls come in pallets, and then they lift them into place. And as a result, these homes have much greater precision, and the precision of their construction allows the homes to be tighter and more energy efficient, um, and also more cost effective. So one of the things that they bring um, into the game of housing is not only the efficient envelope, but they also are very innovative in often giving customers the choice of solar or solar plus storage on homes. And so and on this coming Saturday, they're giving an open house on a home that has both the solar and storage component. And they'll also demonstrate a power shutoff and to showcase just how many appliances and things can still remain running in the home. I'm interested to go. I have no idea what inverter and battery that they've selected to do this with. And I'm very interested to know what inverter and battery they choose. So I'm probably going to attend also. There's the Eventbrite link at the bottom of the slide. You can also search on Eventbrite to find it. I really hope that you guys are able to attend. And Solar Oregon is operated by a shoestring number of paid staff. We have two. I'm not one of them. I am on the board, and I'm also a Solar Oregon volunteer, and I also do a lot of these Green Energy Series webinars. But the operation of Solar Oregon has some overheads that are not, free, and so we would appreciate your donation to help continue to make Solar Oregon activities possible. And feel free to use the chats and Q&A functions of Zoom to ask questions about this webinar. And so about me, so my name is Edward Louie. I work at Pacific Northwest National Laboratory. That's my day job. I work as a building energy efficiency research engineer. It's quite a long title, but essentially I cause trouble in the energy efficiency world of buildings. And outside of work, one of my big projects is to complete an off-grid super energy efficient tiny house that showcases a bunch of the super energy efficient technologies that are out there. And just as a disclaimer, the views in this presentation do not represent the position of Pacific Northwest National Laboratory, U.S. Department of Energy, or Solar Oregon. I've done my best effort to convey facts and information accurately, but you're encouraged to do your own research before you spend thousands of dollars on solar or batteries or anything else. And so for this presentation, we're going to talk about battery-based home energy storage systems, or ESS. And we're going to talk about why the onslaught of new rules, and then we're going to then go over some of the new rules from both UL and NFPA, which is National Fire Protection Association. And then we're going to show that, well, for better or for worse, these rules apply to all lithium chemistries, even though we'll see, as we'll see soon, that some are much safer than others. And then we'll go through some pictures of approved and no longer approved energy storage setups under the new rules, and then we'll do some conclusions. So why all the new rules? Well, often new rules are there because they're a reaction to problems we've seen in the field. And in the world of lithium batteries, there have been a good number of lithium battery fires, ranging from Tesla cars catching on fire, to electric scooters catching on fire, to electric bikes. And there are far fewer energy storage systems that have caught fire, but the number is not zero. One of the most well-known energy storage system fires is one in Australia that took 3 days to put out. And so when you have a lot of energy stored in a very dense way with lithium batteries making that possible, things can happen. And often the cause of the problem is due to a defect in a cell or a defect in the charging system. So what I mean by that is a defect in the cell often is the cause of that is there's metals shavings, typically metal shavings from the manufacturing of the cell, and that metal shaving landed in a spot in the cell that it shouldn't, and that causes a short circuit. And from the short circuit, then you end up having a heat generation when that cell gets charged. And so then that heat generation causes a thermal runaway, and then one cell overheats, and then it catches on fire or overheats adjacent cells, and then those start to, go into thermal runaway, and it becomes a domino effect. Another way that batteries start to catch fire is due to somehow a defective charging controller that allows the cells to be overcharged. A working charge controller will monitor the voltage to keep the voltage of the individual cells from getting overcharged. And additionally, the battery management system has temperature sensors peppered throughout the cell pack. And if any of the cell regions reach a temperature that's above the safe limit, it'll stop charging. Those are the ways it normally, keeps the lithium battery healthy and working correctly. But when some electronic failure happens, sometimes it fails in a graceful way and just stops working. But once in a full moon, it will fail in a way that causes the battery to overheat and go into thermal runaway. And so because there are enough examples, the regulators and rule makers at UL and NFPA have created these rules that we'll look into to regulate batteries, and particularly batteries that are for home energy storage. So UL is one main organization that creates rules and regulations, and they also do a lot of research around the safety of batteries to try and understand, the cause of, why they're catching on fire, and ways to make it safer. And they also have a testing wing that does fee for paid service. You pay them to test your product, to test your battery, and they'll give you a report on the findings and then also give you a seal of approval. You may have seen this logo UL listed on products, and UL has rules and also testing for everything from extension cords to whatever, like blenders. They test all sorts of stuff. UL used to be called Underwriters Laboratories. Now they have rebranded themselves as UL Enterprise. And the reason why they've done this rebrand is so that they can reorganize their company so that the different components that they do are more clearly delineated. For example, UL Research, UL Standard Engagement, and UL Solutions to more clearly define these different roles. So in the world of the hundreds of UL certifications and standards, the ones that are relevant to batteries are these following ones. The UL 1642 defines a series of tests to test the individual battery cell against shock vibration. One of the more, the long list of tests, the ones that are more interesting are ones such as the short circuit test, where you take a battery cell and just dead short it and then see what happens. Some cell chemistries will explode in a very dramatic fashion. Others, when you short circuit them, they just do very little. It's very anticlimactic. And then also there's abnormal charging. So like, if the battery management system goes berserk, then it overcharges the battery. What will happen? That's another test. Those similar tests are done also at the module level. So like when you put a bunch of cells together into a pack or a module, then the UL 1973 test does those similar tests at the module level. And one of the things they test is whether the battery management system can actually successfully, for example, in a short circuit situation, can the battery management system keep the battery pack safe? And then also, what happens if that battery management system somehow fails catastrophically in a way that results in the cell pack being short circuited or charged beyond its safe limits? Then what happens to the whole cell pack? Those test methodologies and are written out in the UL 1973. And then most interesting of all is the UL 9540 series of tests. So these are what's called like large scale fire testing of lithium batteries. And so you would get a module and set it on fire. And then to understand how the fire will propagate from cell to cell or from module to module. And the fire testing procedure is outlined in the UL 9540A standard. And that test procedure will then, the findings of the outcome of the findings from that test procedure are written out in a UL 9540 document to write out the results. And so here's some video of, for example, the overcharging procedure that's done for the UL 1642 standard for battery cells at the cell level. So here we show a overcharging of a lithium polymer battery. So these are the types of batteries that are in your laptops and cell phones. The lithium chemistry of these types of batteries allow you to store about the most energy you can possibly store in a lithium battery. But the downside to storing a lot of energy is that the chemistry is quite volatile. And so it's very, very important that the battery management system, your laptop or phone, controls and monitors the battery to keep it from thermal runaway. Because as you can see in this video, when they do get overcharged, they fail in a pretty catastrophic and spectacular fashion. And it's one thing to have a pouch the size of the battery in your cell phone or laptop blow up, but if you were to use this chemistry in a battery that is big enough to power a house, you can imagine how big the boom might be. And so that's why this type of chemistry, pretty much every manufacturer of home batteries, energy storage system has moved away from this chemistry to a safer chemistry. So here's another battery chemistry. And then this one here is lithium iron phosphate in the yellow one. And so for example, like overcharging a lithium iron phosphate chemistry is fairly anticlimactic. Let's go scroll over there. So there's a side-by-side comparison. So as you can see, with like a lithium iron phosphate, or in this case, a lithium, I think it's a titanium oxide chemistry. Those chemistries are, they don't actually, no flames get erupted from overcharging. They just swell a little bit, and then that's kind of the end of it. Fairly anticlimactic. And so if feel free to later watch this video or find this video on YouTube on your own accord. But this is the test at the cell level. And we'll go on to the other one. So this one is at the module level. It's very similar array of testing, overcharging, short circuit. And for example, like this guy here is showing him dead shorting a pack of lithium iron phosphate cells. And the reason why he's more than happy to stand right next to the cell and dead short it is because there is a working BMS that's protecting the cells, and therefore when you use a dead short, it's able to disconnect the batteries to prevent a thermal runaway. He does explain in this video that if the BMS was not present and you just dead short the cells, that he would not be willing to stand next to it to do the test. And I wouldn't either, because the failure could be much more dramatic. So and that's just the short circuit test. There are other tests that can be done, that need to be done. The UL 1973 test outlines these tests, and they're all done, and they come out as a report on the safety of what they find from these different tests in the 1973 report. So yeah, you get some sparks from the shorts, but it's not like, a whole thermal runaway or anything like that. So the UL 9548 test is a way to evaluating thermal runaway fire propagation. And so this test, as you can see in the far right picture, there is a certain test, the chamber, a setup, and then how this test works is they disable any battery management system. They deliberately overcharge one cell in the module. And in addition to the overcharging the one cell in the module, they also have an ignition source. So they have basically a little torch or a flame, an open flame near the overcharge, the cell that they forced to overcharge, to get to any gases that come out of the overcharged cell, a ignition source to get the fire going. And then the test will look at how that fire propagates throughout the pack. And this test is very specific because in that if you were to test the individual module, so for example, one of these rack mounted batteries, if you were to get that tested, what you'll get is a report that tells the findings from that module, that one rack mounted battery. Now, if you were to then sell that battery in a server rack where you put 6 of them in a server rack, that does not mean that the server rack with 6 batteries is UL 9548 certified, because it's a different configuration. And so the UL 9548 test, you can find test results for both the single server rack battery, for example, and then if the company chooses to test it in, for example, a 6 battery in a rack configuration, they can have a separate 9548 certification for that setup. And if they don't have one, then you will see in later slides that there are rules on how many of these batteries you can put how close together. And so here's an example. Okay, so like the company Simplify, they did a test for the individual module, and then there's some tests concluding that this lithium iron phosphate cell did not create unlimited thermal runaway, so it's safe. And then they also did the same test at the rack level where they overheated the one battery in the rack. And then they also found some results that, the heat transfer to adjacent batteries, they recorded how that works. But wait, there's more. So we'll see later that there is a rule from NFPA that batteries can only be up to 20 kilowatt hours per area. And then if you want more batteries, you would have to put the next group of 20 kilowatt hours, up to 20 kilowatt hours, 3 feet or 36 inches apart from the other battery to keep the domino effect of one battery unit from heating up the next unit and causing a problem. But if you want to have the batteries be placed closer together, so the units be placed closer together, so closer than 36 inches or 3 feet, you would need to do another UL 9548 test where you put the batteries closer together, overheat one of the cells in one battery unit, and then see how the heat and fire propagates to the other units, and then record how big of a boom or how big of a flame or how much smoke gets generated from that situation. So it's very nuanced in what's it called? The number of tests that needs to be done. 1 second. Okay. And so these tests are required. So at the rack level, and then if you place the racks closer than 3 feet, you need to do another test. These tests are required, even if the test results will be fairly obvious from testing each, for example, rack mounted battery. So like here's an example. This battery here, this server rack EG4LL battery, they did a test, and UL 9548 test, and they found the summary of the test is thermal runaway is contained by module design and no flames was observed during the test. Okay, so no flame was observed during the test. So if we were to stack, 6 of them in the rack, theoretically, then with the findings from this burning of one module, you would think that the other 5 modules in the rack would be fine. Well, that's not good enough. The UL 9548 test is such that you would need to do the same test with a rack full of 6 batteries, even though the findings of one, it seems to be pretty obvious what would happen when you stick adjacent batteries to the system. And so then those are the test procedures at the cell level, the module level, and then also then if you were to put them in racks, there's the different UL test requires. NFPA is a organization that is more closer to like how you take the test, those UL tests, And how does that apply to actual rules pertaining the placement of batteries in the home? Like, can you put them in the garage, or do you have to put them outside? And for example, the 3-foot separation rule, that's actually an NFPA rule. So how NFPA decided on the 3 feet separation is that they looked at the test data from the UL test results, the test reports, and they're like, okay, we've read, a dozen of these reports now. So, and we watched a video of how the flames propagate or don't propagate. And so we're going to set 3 feet as kind of the number that we think is appropriate to keep one module from, if it catches on fire, the flames won't be close enough to the other module to, catch that one on fire. And so they come up with those stuff. And these are consensus codes based on, hearings, committee hearings of fire marshals and fire research people. And so NFPA, they wrote out a standard called NFPA 855 that is titled Standard for the Installation of Stationary Energy Storage Systems. And if you read that document, they tell you kind of how many kilowatt hours you can put where in the home. So, and that's kind of summarized in this graphic here. So the current NFPA 855 rules is that you can put up to 20 kilowatt hours of batteries in one kind of container, whether that be a rack or a fully contained, turnkey solution. For example, if the Tesla Powerwall was 20 kilowatt hours, you can put one on your home. But if you were to put more than 20 kilowatt hours, then the next one would need to be 3 feet apart. And if you were to put it inside the home in a utility closet, a storage area, or a utility space, you're allowed up to 40 kilowatt hours. But if you were to put it in a garage, you can have up to 80 kilowatt hours. And if you were to put it outside, you were allowed up to 80 kilowatt hours. And then there's also a caveat in this as well, where if you have a room that is sprinklered, then you're allowed to put up to 50 kilowatt hours per area, and then space that 50 kilowatt hour 3 feet away from the next, 50 kilowatt hour, up to the 80 kilowatt hour maximum or the 40 kilowatt hour maximum. So I guess that 50 kilowatt hour maximum would really kind of only affect you if you were putting in a garage, because like, look at this requirement. If it's inside, you're up to 40. So, that doesn't really apply. And this NFPA 855 standard, they cite the UL 9540A test requirements, and they say, well, you need to put them 3 feet apart unless some battery manufacturer did a UL 9540A test saying that, if you put them closer together, it's still safe and the fire doesn't, grow to a tremendous size. And so once again, that'll be like a test like this, where you have, two 20 kilowatt hour racks of batteries placed 12 inches from each other. So a test like that, you would need to have a test report in order to get away from the 3 feet minimum. And so in an area where you have vehicles that can, back into or hit the batteries, like in particular garage or driveway, you're required to have bollards to protect the batteries. And then if it's inside a garage, you need to have a heat detector and also a vent. A vent to, allow the battery, if it were to catch on fire or overheat, and then the way modules typically, even if there's no flames shooting out of the battery, when they overheat or go into thermal runaway, oftentimes they degas and produce a lot of toxic gases that aren't really good to breathe. And so then you need to have a vent for the gas to escape out of that space. And you're also required to drywall the area, walls and ceiling of the area that the battery is in. And you need to not use 1/2 inch drywall for the walls, but you need to use 5/8 inch drywall, which is a type X drywall that's typically used in ceilings, but you also have to use in the wall as well. And you also need to have some labels and some what's it called, emergency shutdown instructions within line of sight of the batteries. So those are some of the rules that NFPA 855 has implemented. And as you'll see in some of the videos showing the comparison of ranging from dramatic explosion to very anticlimactic problems when you overheat batteries and or short circuit them. Doesn't matter. Currently, the code is that if it's a lithium battery, you have to do the NFPA 855 rules and the UL testing. Even though there are chemistries like lithium iron phosphate that there are really not that many good examples of lithium iron phosphate batteries failing in a dramatic fashion, because you can drill a hole right through one cell and it will not blow up fantastically. So like it's a very safe chemistry. But right now, the NFPA and UL doesn't care about that. You can have lithium iron phosphate battery home energy storage systems, and you still have to comply with those rules. I'm not thrilled about that, but that is what it is right now. And so here are some examples now. So, Tesla, for example, one of the most famous home energy storage systems, in their marketing material, they show a picture of 3 of their Tesla Powerwalls stacked together. Under the new rules, that this is not allowed technically, because each Powerwall is 14 kilowatt hours. You stack 3 of them together, you end up with more than 20 kilowatt hours per unit, which is over the allowance. And then also, Tesla has not actually tested their Powerwall with 3 of them stacked together to the UL 9548 test. Sure, if you look at the Tesla specs, they list that their battery is UL 9540 certified, but that's only with 1 Powerwall. And as shown in the other slides, when you start stacking 2 or 3 of them together, that's a new configuration. And so new configuration requires its own separate UL 9548 test. And so that data is not available. So currently, if a jurisdiction actually follows these rules, then the fire marshal or building department's authority having jurisdiction does not have any data to test data to read and understand, well, how big of a boom, how big of a fire, how much smoke will get generated if 3 of these Powerwalls were stacked together and one of them goes in thermal runaway. And so since there's no data, being a really risk-averse society, you might not get a AHJ or a fire marshal to just blindly trust that, the test results from 1 will then translate to having 3 stacked together. Okay, well, here's another example. This is a configuration you see quite often. 2 Tesla Powerwalls put right next to each other on a side-by-side fashion. So this again will not be allowed in the new requirements, because each of them is 14 kilowatt hours. You put 2 right next to each other, that exceeds the 20 kilowatt hour per unit allowance. And so the requirement now is that you need to space these Tesla Powerwalls 3 feet apart. Then it would be allowed. All right. What about this example? Well, I was disappointed to find out that, yes, this battery is UL 9548 tested at the server rack, individual server rack battery, but they have not done the test for 6 of these batteries stuck into a server rack and to test them as together. And so this configuration in the rack, it has not been 9548 tested. And even though, as I showed you the report from the individual battery test, there's no flames emitted from 1 battery, so it should be safe. But again, it doesn't matter. That's not good enough. You still have to test it. All right, so what about this setup? Well, this setup would be approved because in this case, each of these batteries are 5.12 kilowatt hours. So 3 put together is still below the 20 kilowatt hour limit. And as you can see, they've placed each of the units 3 feet apart from each other. And so therefore, this would be allowed under the NFPA 855 rules. If this was in a vehicle driving area, then it would need bollards. But this particular deployment, there is no vehicles driving in this area, so therefore bollards are not required. So I actually had a hard time finding a picture of battery installed that actually meets the NFPA 855 requirements. Yeah, because there's so many batteries pictures are like these, and these are no longer approved under the new rules. So that's what I'm saying. These new rules are very impactful, and that brings us to one of the conclusion points, which is that a lot of the pictures you see of batteries setups in the field are no longer really allowed under the new rules, or they can't be installed exactly the same way. You need to do some modifications like space them further apart. These new rules will likely increase the planning and installation costs of home energy storage systems. The number of tests, like for example, like I said, if you put the different permutations, you need to have its own separate UL 9548 test. So these additional test requirements will likely increase the cost of the batteries. But thankfully, the number of batteries that even have undergone a 9548 test, the number of batteries is actually quite big. That all the big name players in the world of home batteries have undergone UL 9548 testing, at least at the module level. The number that have tested it, if you were to put them close together or stack them more, like 3 or 5, 6 stacked together in a server rack, those tests have not been done yet. But hopefully, those manufacturers will do these tests soon, and then therefore we can, install them stacked together in these different configurations. And then also, hopefully, more of these battery manufacturers will test them in a configuration where they're placed closer than 3 feet apart, and then certify that it's approved to be placed up to, like, for example, 0 inches apart. Like Simplify has certain batteries where it's approved to be 0 clearance from each other, so you can butt them right next to each other. But that's just one manufacturer that's done the test. Many others have not. And also keep in mind the NFPA 855 standards and these UL test standards. These are not necessarily set in stone. These are the current rules. Future committee hearings might find that, oh, well, the industry, has come back and determined that, we've gone overboard with safety, and that in real life, we don't need to go to this level of safe in order to be safe. And so there could be future versions where it's less arduous and difficult to properly place the batteries according to the current rules. There may be that future. I don't know. So that's kind of the findings that we have right now with regards to home battery energy storage systems and the current fire codes. These current fire codes are cited in the 2021 International Residential Code. So if you live in a jurisdiction that has adopted the 2021 residential energy codes, if the authority having jurisdiction wants to enforce this particular area of the codes strictly, then yes, all those diagrams of installation requirements applies. Right now, what we're hearing is that, like, there are jurisdictions that have adopted the 2021 International Residential Code, and there are varying levels of enforcement in regards to these, like, spacing requirements and how many kilowatt hours you can have in one unit, stuff like that. Some cities are very strict and others are very loose. it's a bit of a wild, wild west right now, because even though it's the 2021 International Residential Energy Code, a lot of jurisdictions didn't start actually adopting it until 2022, and then sometimes they have a phase-in period, and so now we're at 2023, and this stuff is starting to actually hit actual projects. So, very interesting findings. To
Edward,
bring awareness.
there is a question in the Q&A specifically about Portland. Does anyone have experience with City of Portland local jurisdictions applying these standards? Do you know anything about what's going on right here?
I don't have any recent experiences. I just have experiences and stories from before this new requirements were adopted. And that was in the wild, wild west days when you can basically do whatever you want. But now that, Portland, Oregon has adopted the 2021 code, I don't know how the enforcement in terms of, like, for example, bollards and spacing and venting and stuff, drywall thickness and all that stuff is. One thing I do know is that if the previous energy storage system was permitted and approved, it is grandfathered in to, so therefore, like, you don't need to, upgrade the safety requirements of that area to the new code. The only thing that could change that is if you were to, like, add additional batteries to an existing home battery energy storage system, and that might trigger the entire setup to need to be up to the new code. So that's the extent that I know about Portland and codes in general. Okay. Okay, and any other questions? None. Okay, well, I'll put a plug in for the next Green Energy series, which will be on July 1st at 10. And we're going to talk about solar and carbon, specifically the interplay between operational carbon and embodied carbon. And so how does this work is that, like, you buy solar panels, you put it on your roof, and you offset your energy use during the day. So you're not using electricity from the grid that has a certain carbon attached to the kilowatt hour you buy from the grid. So when it's sunny during the day, you get like zero carbon operation of carbon energy. But then if you only have solar panels, then at night and in the wintertime, you're buying a lot of kilowatt hours from the grid. And each of those kilowatt hours comes with a certain carbon attached to it. So that contributes to your operational carbon. If you were to buy a battery, then that means at night, you also get to use your carbon-free energy that you generated during the day at night also. So then that reduces your operational carbon. But the battery, obviously, they had to mine lithium and iron and all this other stuff in order to make the battery. So you're going to end up with a system that has a higher embodied carbon. And then oftentimes, if you design that just for the net zero, what will happen is you over-generate during the summertime, but then in the wintertime, you really under-generate. And so then you still have to buy a sizable amount of kilowatt hours in the wintertime to cover your energy needs. And the way carbon works is just because you generated excess zero carbon kilowatt hours and sent it to the grid during the summertime does not magically mean that you get zero carbon energy that you can buy off the grid in the wintertime. That's not how that works. In fact, the power company also struggles to produce clean energy during the wintertime too, because their solar panels aren't actually producing much at all either. So, okay, then what about the third scenario? If you buy a bigger battery and a bigger solar system so that even in the wintertime, you're able to generate most of your energy use. But then when you buy a bigger solar panel, a bigger battery, then you have a bigger embodied carbon. So how does this all play out in terms of, how low carbon you can get under these different scenarios? We'll explore that July 1st at 10 a.m. And that's all I have for this Green Energy series. I hope you enjoyed it and found it useful. And then I'll look to see if there's any additional questions.
I don't see any. Thank you so much, Edward, and thank you for doing this from a car driving you to a conference. It's working great. Your Android system of connection seems awesome. So
Okay.
see everybody next month. Thanks for coming, and I will push end. Thank you.
All right. Thanks, everybody,
Okay.
and take care.